It began in silence beneath a sky the world had stopped watching. On the night of September 11, 2025, while observatories worth billions slept under the illusion of routine, a lone amateur in Ukraine captured something so luminous it defied logic, a greenish-blue eruption of light that seemed to split the night in half. His name was Vladimir Bitzikli, and what he recorded wasn't a glitch or an atmospheric illusion. It was a comet brighter than 10,000 power plants, combined stretching wider than 5 full moons. He called it Swan. Within hours, astronomers realized what he had found wasn't just another icy wanderer. It was a phenomenon powerful enough to challenge the interstellar visitor known as Three-Eye Atlas. For the first time in modern astronomy, a backyard telescope had outperformed the world's largest observatories. The discovery forced one question: how could a global network of automated sky surveys, supercomputers, and space-based detectors miss a celestial event of this magnitude? Bitzikli's modest laptop glowed faintly in the dark as he analyzed hydrogen maps transmitted by NASA's SOHO probe. He noticed a strange turquoise plume forming in the constellation. Virgo, an unmistakable chemical signature that didn't belong there. It wasn't cosmic noise. It was a living object, venting gases at a scale rarely seen. Over the next few frames, that plume expanded exponentially. He ran scripts to isolate artifacts, eliminated optical errors, and once convinced, filed a report with the Minor Planet Center at 1:30 a.m. Within hours, his finding ignited a chain reaction in the scientific community. Confirmation came from Martin Mašek's team at the Fram telescope in the Czech Republic. The object was real. The data showed a brightness magnitude of 7, visible to anyone with a basic 50-millimeter binocular lens. For a modern comet, that was almost unthinkable. Overnight astronomy had been democratized again. But what made Swan truly extraordinary wasn't just its brightness. It was what it revealed about the fragility of cosmic observation itself. By September 12th, orbital predictions indicated the comet would pass the Sun at just half an astronomical unit, roughly 75 million kilometers, the distance between Earth and Venus. And 5 weeks later, on October 19th, it would cross Earth's orbital plane at only 0.26 astronomical units, just 39 million kilometers away, well within Mercury's orbit. At that range, the tail could stretch across 5 degrees of the night sky, 10 full moons laid side by side. The comet was radiating energy equivalent to 1,000 gigawatts, matching humanity's total daily production. In essence, Swan had become a floating power station, blazing through the void, emitting more light than entire cities combined. For stargazers, it was a spectacle. For scientists, it was a race against time. Every hour before its closest approach mattered. Yet even as the comet's magnitude intensified, comparisons began to surface, because Swan wasn't alone. Another traveler dimmer, but far more mysterious, was already cutting through the solar system at unimaginable speed. The interstellar object, Three-Eye Atlas, detected earlier that year, was on a hyperbolic trajectory with no return. It was smaller, colder, and nearly invisible, its brightness over 300 times weaker than Swan. But its speed, 58 kilometers per second, enough to cross from New York to London in under 2 minutes. One was blazing and local, the other silent and alien. Together, they turned the sky into a laboratory of extremes, a clash between brilliance and mystery, between what we see and what still hides beyond the light. And as astronomers rushed to track both, one chilling prediction began circulating in closed forums: Swan and Three-Eye Atlas were approaching an intersection point just 47 days apart. Was this pure coincidence or the beginning of an interstellar convergence no one had foreseen? Within hours of the discovery, observatories across Europe, Asia, and the Americas scrambled to recalibrate their instruments. NASA's Near-Earth Object Office cross-checked Bitzikli's coordinates, while independent astronomers flooded online networks with confirmations. Suddenly, the hierarchy of discovery had collapsed. One man armed with a modest telescope, and persistence had outpaced the global scientific machine. The comet's behavior was erratic. Its core or nucleus appeared to fragment under intense solar radiation, releasing jets of gas that created the enormous green-blue plume seen from Earth. That hue came from ionized carbon and diatomic oxygen, an unmistakable signature of volatile compounds reacting under sunlight. But it wasn't just beautiful, it was volatile. The more it glowed, the more unstable it became. Astronomers speculated that Swan could disintegrate before its closest approach, releasing massive dust clouds across the inner solar system. Meanwhile, 3I Atlas remained a phantom presence. Detected months earlier on a hyperbolic path, it was moving at a velocity that defied the Sun's gravitational grasp. Observations from the European Southern Observatory revealed something extraordinary in its spectrum, a CO2-to-water ratio of 8:1, and traces of nickel gas, a composition almost unknown among comets, formed within the solar system. This meant one thing: 3I Atlas had originated far beyond our planetary neighborhood, possibly from a dying star system or a molecular cloud outside the heliosphere. The object was small, nearly invisible, but scientifically priceless, a chemical time capsule from another galaxy. Then came the data blackout. On October 8th, both Swan and 3I Atlas slipped behind the Sun, falling below the 20-degree safety threshold that makes direct observation impossible. For 11 days, the global telescope network went blind. No images, no spectra, no real-time tracking, nothing. The timing couldn't have been worse. Swan was nearing its closest point to Earth, and 3I Atlas was at peak outgassing. It was as if the universe had drawn a curtain over its stage at the most critical moment. Simulation models attempted to fill the gap. The Minor Planet Center estimated Swan's orbital period at 1/400 years, a visitor returning roughly once every millennium. NASA, using different parameters, predicted 20,000 years. The gap of 19,000 years wasn't just a mathematical discrepancy, it was a reminder of how fragile our models still are when built on weeks of incomplete data. During this blackout, something remarkable happened. Thousands of amateur astronomers worldwide began to collaborate, exchanging measurements, images, and predicted orbital paths. Citizen science and institutional science merged into one global experiment. Backyard telescopes became part of an unplanned planetary network. The universe was no longer a stage reserved for experts. It was a collective mystery open to anyone with curiosity and patience. As light from Swan slowly reappeared from behind the Sun, a new question emerged, one that blurred the line between coincidence and cosmic design. Why did two unrelated objects, one born in our solar system, the other from deep interstellar space, emerge in the same season on nearly converging paths? When both comets finally re-emerged from solar conjunction, astronomers were stunned. Swan had survived its close encounter with the Sun, but it wasn't the same object anymore. Its tail had stretched into a colossal arc 5 degrees across the sky, visible to the naked eye even from city edges. Photographs taken from Australia, Chile, and Japan revealed an immense emerald veil sweeping across the stars, rippling like a storm in slow motion. The scale of the event rekindled public fascination with the cosmos, something not seen since the days of Hale-Bopp or Neowise. Yet beneath the spectacle, scientific teams were split. Some believed Swan's energy burst was a natural reaction to solar heating. Others suspected a deeper anomaly, an instability in the comet's core composition, hinting at materials foreign to known solar system chemistry. The debate intensified when data revealed intermittent electromagnetic fluctuations around Swan's plasma tail, tiny but measurable deviations in ion density that didn't correspond to standard solar wind patterns. NASA labeled it plasma turbulence. Others called it something we do not yet understand. Meanwhile, the faint traveler 3I Atlas became the focus of interstellar research groups. Its brightness remained minimal, but its scientific weight was enormous. Traveling at 58 kilometers per second, it crossed a path that theoretically intersected the outer plane of Swan's orbit, just as predicted. The convergence never became a collision, but the timing was uncanny. 47 days separated their closest points. As one blazed through the inner solar system, the other exited it forever, leaving a wake of chemical signatures that didn't belong to any known class of comet. The European Southern Observatory reported high concentrations of nickel vapor, a metallic gas that typically requires extreme heat to form. That discovery sparked questions that reached far beyond astronomy. If 3I Atlas carried metallic gases forged in stellar furnaces, could it have originated from a planetary core torn apart eons ago? And if so, was it evidence of cataclysmic events outside our solar boundaries, remnants of civilization's suns long extinguished? The notion was speculative but irresistible. Scientists tread carefully, but online forums exploded with theories linking 3I Atlas to previous interstellar visitors like Oumuamua, whose erratic motion had sparked years of controversy. Could both belong to the same cosmic family, a chain of ancient fragments drifting between star systems? While official statements dismissed such connections as premature, the public imagination had already taken flight. What truly amplified the tension was the timing of the blackout. Between October 8th and 18th, while both comets hid behind the sun data streams from several deep space observatories briefly went offline. Though likely coincidental conspiracy circles began circulating claims that NASA had withheld observations, fueled by the fact that when communications resumed, no one could account for the exact trajectories during those missing days. The agency later explained it as routine telemetry interference, but that didn't stop speculation. In science, timing is everything, and coincidence is the mother of suspicion. Beyond the noise, a quieter realization spread among professionals. The 2025 comet season had changed how discovery works. A man in Ukraine had beaten multi-billion-dollar systems, not through luck, but through persistence, intuition, and curiosity. Bitsukley's discovery proved that science isn't just about access, it's about attention. For him, the universe wasn't silent. It was speaking to anyone patient enough to listen. As October faded into November, Swan dimmed, retreating from the inner solar system, its once blazing arc dispersing into a faint, ghostly thread of dust. But its legacy endured not merely as a comet, but as a challenge to the system of discovery itself. Data from the Czech Academy of Sciences confirmed the maximum brightness reached magnitude 6.2, visible with binoculars, while the interstellar 3I Atlas remained 360 times dimmer, accessible only through advanced telescopes. Both had vanished behind the sun during their most active phases, creating an irreversible gap in observation. That blackout now stands as one of the most frustrating blind spots in modern astronomy. Between speculation and certainty lies the realm of mystery, and 2025 had plenty of it. The discrepancy between orbital period estimates from NASA's 20,000-year cycle to the Minor Planet Center's modest 1,400 years revealed how fragile our celestial models truly are when based on fleeting weeks of data. It reminded scientists that our technology, as advanced as it seems, still depends on moments of human vigilance, the kind of vigilance that allowed an amateur astronomer to rewrite the script of discovery. In retrospect, the simultaneous appearance of Swan 3I Atlas and even a third dimmer body dubbed Lemon marked not just a scientific event, but a cultural one. For a brief moment, the heavens became a shared experiment uniting professionals and enthusiasts across 3 continents. It wasn't just science, it was collaboration, curiosity, and awe all converging in the same night sky. The media focused on spectacle, on the green blaze seen from rooftops and deserts. But deeper within the data lay something more profound, a reminder that the universe is neither predictable nor domesticated. It hides wonders in plain sight, waiting for eyes willing to see what automated systems overlook. Bitsukley himself said later in an interview, "I wasn't looking for fame. I was looking for the feeling that something vast was out there, moving alive." His words resonated with millions who watched Swan's trail fade into darkness. Because in the end, the story of Swan and 3I Atlas wasn't about collision or catastrophe, it was about perspective. About realizing that even in an age of artificial intelligence and robotic telescopes, the human element, the capacity for wonder, remains irreplaceable. The cosmos still rewards those who look up, not because they expect answers, but because they dare to ask questions. And as both comets vanished into the silence beyond our reach, one question continued to echo through observatories and living rooms alike. If we could miss something as bright as Swan, what else might be moving out there right now, unseen, unmeasured, and waiting to remind us how small we truly are?